Well, we're dealing with solubility and solubility equilibrium again. And we're going to be dealing with this mineral, hopeite. Interestingly, it was discovered by Thomas Hope, he got to name it, who also ended up discovering strontium and that the maximum density of water was 4 degrees Celsius. In addition, Charles Darwin considered him to be his favorite teacher. Zinc phosphate is used as a coating for metals to provide corrosion resistance and protection from wear. All right, let's go to the problem. Here's the question. We've got the KSP, the solubility product constant for zinc phosphate, 9 times 10 to the negative 33. That's a real low solubility. So it's not going to dissolve much, but we want to find out its molar and mass solubility. Now, typically in FRQs, when you've got a compound this complex, they'll give you the molar mass, so you don't have to waste your time calculating it. And here it is, a hefty 386 grams per mole. Now, on to the problem. We have the equation for it dissolving, and we've got to use these subscripts. We have 3 atoms of zinc becoming zinc ions, and you should memorize that zinc has a charge of +2. It's one of the transition metals that has a constant charge when it's an ion, and that and silver are 2 notables, silver being +1. And we've got the phosphate polyatomic ion, one that you should know too. It's got one of the few polyatomic ions with a charge of 3 negative. I didn't bother putting the aqueous in the equation here because we know it as ions. So we're going to dissolve this. We're going to use our beautiful ice chart, initial change and equilibrium. And we're going to start with what we refer to as the molar solubility, a lowercase italicized s, and we're putting it in water. Our concentrations of zinc ions and phosphate are going to be zip, nothing. If we had put this in a solution of zinc nitrate or sodium phosphate, then we'd have some concentrations to start off with, but not in this case. We're just dealing with water, which is what molar solubility is about. The molar solubility is how much of this zinc phosphate will dissolve in a liter. So we've got our change in moles. We'll lose all this molar solubility, but we've got some important coefficients here. We will get 3 times that molar solubility for the zinc because of our stoichiometry, 1 to 3, and 2 times our molar solubility to get the phosphates. One of these zinc phosphates will produce 5 ions. That's a pretty significant thing. So at equilibrium, we've got none of these solids zinc left because we said all of it's going to dissolve. That's its molar solubility. Here we produce 3s and 2s, and here's our equation for our solubility product, which is zinc concentration, phosphate concentration. So we would, in terms of molar solubility, figure out that we've got a 3s cubed and a 2s squared. This is pretty solvable. Here I've got the equation. They gave us the molar solubility, 9 times 10 to the negative 33, pretty small value, and then we calculated this from our ice chart. Now, a quick look at it. We're going to realize that we're going to have an s raised to the 5th power, and so if our answer is going to be 5 divided into this negative 33, so we'd expect maybe either a 6 or a negative 7 to be the range of our answer. But let's get the calculation going. Well, I've got my calculator up, and let's see if we can solve this. I presume your math is going to be pretty good, so we're going to be solving for S, our molar solubility, so I'll put in is equal to our constant. I won't bother with the times 0. Don't forget our second function e to get that times 10 too, and then the negative 33. Now we'll have to end up solving for S, so we're going to have to involve this 3 cubed, which is 27. We'll be dividing that value by 27. And then we also have this 2, which is a 4, so we'll be dividing that by 4. And that's going to give us this value, or 8.33. It keeps on going probably to the negative 35. But we've got an S, so all we're going to have to do is take the 5th root of it. You don't have to type that number in again. You don't want to type it in again. All of our calculators will chain the value, and whatever this answer is, all we have to do is raise it to the 1 divided by 5 power, and voila, we've got our answer that we would write out as being the molar solubility. Carry that out to 2 significant digits. Now they also wanted the mass, So if we had the moles of material that would be dissolved in 1 liter, we would just multiply that times our molar mass, which was given at 386.1. We won't need the 0.1 because this is going to be the 2 significant digits anyway. So save yourself an entry. That will be your mass of the zinc phosphate that would dissolve in a full liter of water. Not much. This is going to be 0.05 milligrams. Let's get our calculator and try another method of solution, because there's another feature that these TIs and a number of graphing calculators have, and they've got a numeric solver. So I'm going to enter that, see if this will solve things for me. And again, we're going to need our 9 and the second function, e negative 33, is what is going to be on the left side of our equation, what's going to be equal to the right side of our equation, equation 2, because it's a simultaneous equation solver, is going to be, don't forget your parentheses. If you didn't put your parentheses in this, you're going to have to put in the 27, but I can have it do all my solutions. 3 times, I could use the letter S, but then I have to go alpha and find out where S is. So, oh, there it is down here. I prefer to use this. This gives me a nice X quickly, and it stores it in X. It's 1 keystroke. We want to see which is the fastest method. And I'm going to, of course, raise this by cubing it. And then I can put my next parentheses in. I don't need it times. This calculator is smart enough to know that I'll be multiplying this, and then I'll put my 2xs, and then raise that to the second power. That's it. I'm going to double check my equation. Numbers are all in. I've got my parentheses. My math looks good. So I'm going to say this is okay. And I'm going to solve for this. I'll start my solution by looking at 0, because it gradually graphs this thing. We'll have it start at 0. I'll end up, you can use this graph to solve, or you could use a alpha function to solve too. And let's put that entry in. Voila. Same answer. I prefer the algebraic method, the standard method, because sometimes this solver doesn't work, but please don't use it too much, otherwise your math skills will atrophy, because it asks for my molar mass. Since I realized that X was now that answer, I would then multiply by the 386.1 to get the mass of hopeite, or zinc phosphate, that would dissolve in a liter of water. And we've got the same answer. Then again, I would only give this to 2 significant digits. Save your pencil, some of it's lead or ink, because it's only going to be good to 2 significant digits. And putting more than that, reader will say, oh, they don't know what they're doing. And you don't want that. You want to get some respect for your answers. So let's see what that mass would look like. Here's a chemist measuring out about 30 times the mass solubility of that zinc phosphate. This is 2 milligrams, and the mass solubility of zinc phosphate was 0.059 milligrams. It's a beautiful balance, a Mettler XPR, about $31,000 worth of microbalance.